Hi, I'm Ian,
And I'm Avi.
and this is Lab 2 Gaussian Beam Profiling and Propagation. We started by aligning the laser and microscope to our optical rail, just as we did in Lab 1. We observed the beam and microscope reticle on a distant observation screen and centered both on a point that marked initial beam position. We selected a 4x objective for the microscope to allow for sufficient working distance in Part B. After turning the laser off, we looked through the microscope and positioned it such that the reticle was focused on the mechanical aperture of the laser. We subtracted the position of the laser aperture, also called position A, from the position of the microscope to find our microscope focal distance. This distance is just a reference measurement that will be used throughout the rest of the lab to precisely measure the position of the knife edge with respect to the laser aperture. If we focus the microscope reticle on the knife edge, we can use the microscope position and the focal distance measurement from earlier to obtain the position of the knife edge along the optical rail. We call this position B. Subtracting position B from position A gives us Z, the axial distance from the laser. Then we sought to measure the profile of the Gaussian beam using a scanning knife edge. We replace the microscope on the rail with a photodiode. This photodiode will allow us to record normalized optical power transmitted as a function of lateral knife edge position. We started with the knife edge completely blocking the beam, then translated the edge back in increments of 20 microns, recording the power values registered by the photodiode. We did this until the knife edge was completely out of the beam's path, or when the power values leveled off at their maximum value. We then carried out the same measurement procedure for a knife edge location farther down the optical rail.
The power distribution from knife edge profiling the Gaussian beam can be described by the equation shown here. The equation is an error function dependent on the beam radius at the specific z location, wz, and the knife edge scanning position, x. Because we know the wavelength, lambda, and the beam waist, w0, from the laser specs, we can use this equation to plot the theoretical power at the two z locations. The middle equation was also used to find the theoretical beam radii at each location. Here are results from the Gaussian beam profiling using a knife edge at the two locations. The red dotted curve represents our measured data. The blue curve is a theoretical power for the specific distance. The measured radius is the difference of the knife edge locations corresponding to 16% and 84% of the total power, or one standard deviation on either side of the mean power, shown by the solid and dotted lines on the plots. Now that we know the beam radii at two different z locations, we can use this system of equations to solve for the Rayleigh range, z0, and the beam waist. Here are our results. We've been calling the location of the laser aperture z equals 0, but this is just a reference, and not where the beam waist is actually located. Using the Rayleigh range we just calculated, we can solve for the actual distance from the beam waist to the two locations we measured, z1 and z2. We can also solve for the actual location of the beam waist in reference to the laser aperture. We found the beam waist was 3.4 centimeters behind the aperture.
The experimental derivation of our Rayleigh range and beam waist allows us to calculate many important beam parameters. One important parameter is the beam divergence angle, which we calculated as 0.033 degrees. We can also calculate the expected beam diameter and wavefront radius of curvature for any value of z using the equations shown. This capability is vitally important in applications such as free space laser communication because it allows for prediction of beam behavior after propagating large distances. If we introduce a positive lens to the system, it will create a new beam waist along the optical rail. This reproduced beam waist is different from the original beam waist. However, using this method allows us to measure the beam profile on opposite sides of the beam waist. We align the positive lens using the same alignment procedure as we did in Lab 1. When we could observe the back reflections from the lens passing through the iris, we know our lens is aligned. As we did with the laser aperture and the knife edge, we focused the microscope on the rear vertex of the lens to precisely locate its position along the optical rail. We briefly ran into an issue where the microscope could not get within focal distance to the rear vertex of the lens. The movement was barred by the micrometers on the microscope mount translation stage. We solved this problem by sliding the microscope outside the center of the mount, which forced us to realign the microscope and get a new measurement for focal distance. This complication taught us to look ahead in the directions and consider all applications before choosing the method of mounting an optical element. With the lens position fixed, we slid the microscope along the optical rail to estimate the location of the beam waist. When the beam on the observation screen has the smallest diameter, the location of the microscope is approximately the location of the reproduced beam waist. We then profiled the beam again using the scanning knife edge method. We did this for two positions along the optical rail, one before the approximated beam waist location and one after.
Here is our experimental data from the knife edge profiling inside and outside of the beam waist. Using the same procedure as before, we found the new Rayleigh range in the new beam waist as shown on the left. The beam waist was about 3 times smaller than before, however the Rayleigh range was almost 9 times smaller. Z1 and Z2 are shown on the right. Z1 was only half a centimeter, meaning we should have taken the measurement a little closer to the lens. The new beam waist was about 60 centimeters from the laser aperture.
The introduction of the lens resulted in a higher beam divergence angle and beam diameter at a distance of 10 meters. For most applications using lasers, a beam with a small divergence angle and a large Rayleigh range is ideal. In our case, the use of a positive lens to focus down the beam did not lead to lower divergence.